Hi guys, we are students of Viva Institute of Technology. We are going to present here the design of bomb differential. My name is Gaurav Salaskar. My colleagues are
Aniket Sabale,
Dinesh Routela.
These are the guidelines of our project.
Introduction. Design of worm differential. We shall now design a differential using a worm gear reduction around the meter gear set. This is inspired from the Napier worm gear drive invented by the British Napiers and Son before the First World War. Commonly found automobile differential have a reduction ratio of 6 at a max. Most on the road vehicles have differential with reduction of 3 or 4. Most of the manufacturers will introduce an additional single-speed gearbox to increase the reduction ratio. Our design contains worm and worm wheel along with 4 meter gears. Input shaft is connected to worm while output is connected to meter gear. Aim of our project. Commonly found automobile differential have reduction ratio of 6 at a max. This is because of designing an automotive differential with a reduction ratio greater than 6 may lead to a bulky design which isn't feasible to position with a limited space available. Furthermore, increasing the size of the differential may lead to excessive undesired weight. Most of the vehicles on the road differential with reduction ratio 3 or 4. Commercial speaking, finding the differential with reduction ratio greater than 6 close to impossible. Now most of the manufacturers will introduce an additional speed gearbox. However, this would overcomplicate the design and increase the service cost. Thus, the aim of differential with reduction ratio greater than 6 using the worm and bump along with the meter gear. Now, there are two mechanisms which are introduced in our project. First, worm drive, and second is meter gear drive. First of all, we will see worm drive. A worm drive is a gear arrangement in which worm meshes with a worm gear. Drive axis of both worm and worm gear are perpendicular to each other but not intersecting. Vehicle axle transmit the motion to worm which is further transmit to motion worm gear by sliding action between them. Now, meter gear drive. The meter gear is type of bevel gear having velocity ratio 1 and drive axis is perpendicular to and intersecting each other. In this system, we use 4 meter gear attached to worm gear by means of pin shaft. Thus, rotation of the worm gear is transmitted to meter gear. Due to velocity ratio equal to 1, all the meter gears are rotated at same speed and transmit required motion to wheel axle.
In worm differential drive, there are 3 critical components, which are worm wheel, and meter gear. The force analysis is as shown here. The following material are being used for the 3 critical components. For the design of elements, following assumptions are made. Tooth profile, involute tooth profile, pressure angle is equal to 20. We are using carefully cut gear with SN gearing. Tooth system, full depth system. Input power is 6 kW. Input speed is 4100 rpm and reduction ratio is 7:1.
Design of worm and worm gear. Input power is 6 kW. Input speed 4100 rpm. friction ratio, that is I is equal to 7. Step 1. Selecting the service factor. On PHG 7.69. Select the service factor as 1.2. Step 2. Calculating the design power. That is P is equal to 6 into 10 raised to 3 into 1.2. P is equal to 7.2 kilowatt. Step 3. General assumptions. Now general assumption. Shape of the worm gear drive is single envelope. Tooth profile is, that is for worm is helicoid and worm wheel involute profile. Pressure angle is 20 degree. Quality of gear, carefully cut gear. Type of gear is SN gear. Step 5. Deciding the number of start on worm. That is Z is equal to 40 upon I plus 1 and I is equal to 7. Now Z is equal to greater than equal to 5. Step 6. Calculating number of teeth on worm wheel. That is Z is equal to I into Z. 7 into 5, Z is equal to 35. Step 5. Deciding the diameter quotient, and that is denoted by Q. Selecting the diameter quotient on PHG 8.44. Q is equal to 8. Step 8. Calculating the lead angle and helix angle for worm and worm wheel. Now lambda W is equal to lead angle of worm, that is selecting on PHG 8.44, and lead angle, that is tan inverse Z by Q. Now lead angle of worm is equal to 32 degree and helix angle of worm is equal to, that is denoted by beta W, 90 minus lambda W, that is beta W is equal to 58 on PHG 8.52. Now helix angle of worm B is denoted by beta G, which is equal to lead angle of worm, that is equal to 32 degree. The lead angle of worm B is equal to helix angle of worm, that is equal to lambda G is equal to 58 degree. Calculating the virtual number of teeth for worm, which is equal to Z is equal to cos cube beta W, and beta W is 58, and the teeth for worm is 33.60. Now teeth for worm wheel, which is equal to 35 upon cos cube beta G. Beta G is 32 degree. Now virtual number of teeth for wheel is equal to 57.38. Step 10. Calculate the Lewis form factor based upon virtual number of teeth, which is equal to pi into 0.154 minus 0.912 upon virtual number of teeth for worm, which is equal to 0.3983. Now calculating the virtual number of Lewis form factor for worm wheel, which is y, pi into 0.154 minus 0.912 upon 57.38. Lewis form factor for wheel is 0.4338. Now selecting the material. Selecting alloy steel on PHG 1.13 for worm. Now alloy steel is 50 Ni 4Cr1. SUT is 1500 Newton per mm square. Final hardness number is 650 and contact stress is 500 Newton per mm square. Now selecting material for wheel. It's phosphor bronze on PHG 1.9 SUT is 240 Newton per mm square, braid hardness is 70 and contact stress is 80 Newton per mm square. Now deciding the step 12. Step 13. Calculation of actual module, which is denoted by mx, or transverse module mr of wheel. PSG 8.44. The equation is A is equal to Z by Q plus 1 cube root of 540 upon Z upon Q into contact stress whole square into torque, design torque, the moment. Calculating the output speed, which is equal to N2, N1 upon N2 is equal to I, and I is 7. So output speed is 586 rpm. Now calculate the rated torque, which is calculated by power. Power is equal to 2 pi N2 upon rated torque upon 60. Now power is 7.2 kilowatt, 2 pi into 586 rpm into rated torque upon 60. From this formula we got rated torque is 117.32 Newton per meter. Convert into kgf per centimeter is equal to 1.17 into 10 raised to 3. Now design torque is equal to rated torque into kdk. Now this kdk factor we got from PSG 8.44. kdk is equal to 1. Now design torque is equal to 1.17 into 10 raised to 3 kgf per centimeter. Substituting the value in equation of A, and we got A is equal to 19.44 centimeter. From PSG 8.43, we calculate the axial module. The formula is A is equal to 0.5 into mx bracket diameter coefficient, that is Q, plus Z plus 2 into x. A is equal to, just now we calculate A is equal to 19.44 into 0.5 into mx, diameter coefficient 8, Z is equal to number of teeth, that is 35, and 2 into x. Now axial module is 0.904 centimeter, which is 9.04. Selecting Q into Q is diameter coefficient, mx is axial module. Now B is 6. Now the beam strength is 772.51 kgf. Now step 15. Equation for the dynamic load is 6 plus Vmg, that is velocity, speed upon 6 into Ft on page 8.52. Now speed for wheel is pi d and pi d2 n2 upon 60. d2 is calculated by mx into axial module into z. 10 into 35 is 3350 mm. Put in the equation of speed, and we got speed is equal to 10.73 meter per second. Now from PSG 8.57 we calculate the tangential force, which is equal to 2 into design torque upon d2. Now d2 is 35 and design torque is 1.17 into 10 raised to 3. From this we got tangential force 66.85 kgf. Put in the equation of PSG 8.52, 6 plus Vmg upon 6 into Ft, and we got dynamic load is 186.40 kgf. Now the dynamic load is less than beam strength, So our design is safe in dynamic loading. Check for the wear load. The equation for wear load is PSG 8.52, which is wear load divided by FW. Now DG into P into power in kilowatt. Now the step 16, check for the wear load. From PSG 8.52 we got the equation for wear load. FW is equal to diameter of the wheel into face width into KW. That KW factor we got from PSG 8.54. KW is 5.6. Now wear load is 1176 kgf. The wear load is greater than the dynamic load, so design is safe. Step 17, calculating the gear proportion from the PSG 8.47. We calculate the gear proportion for the both worm and worm wheel. First calculate the pitch circle diameter, that is D1 is equal to 18 mm. And for wheel D2 is equal to 35 cm, that is equal to 350 mm. Now tip diameter for worm, which is denoted by DA1. DA1 is equal to D1 plus 2FO into axial module. DA1 is equal to 100 mm. And tip diameter for the worm wheel is DA2, that is 370 mm. Now calculating the root diameter for worm, that is DF1. Formula of DF1 is equal to D1 minus 2FO mx minus 2 into C, and C is 0.25 into mx. Now DF1 is equal to 55 mm. Root diameter for the wheel is 325 mm.
Now see the design of metal gear. As we know, metal gear is a type of pure gear having reduction ratio 1, that is having equal number of teeth on pinion as well as on gear. The shafts are positioned at right angles to each other and are intercepts. Here input speed for the metal gear is 5.71 rpm. Step 1, selection of service factor. Here we are assuming service factor is equal to 1.2 from PSG data book. Step 2, calculating design power. Design power is equal to rated power into service factor. Rated power is 6 kilowatt and service factor is 1.2. Therefore design power is 7.2 kilowatt. Third step is calculating number of teeth on gear. As velocity ratio for meter gear is 1:1 and we are assuming pressure angle is equal to 20 degrees. Therefore number of teeth on gears is equal to 70. Step 4, calculating semicone angles for gears, that is delta. Tan delta is equal to sin theta upon I plus cos theta. Here theta is equal to 90 degree. Therefore delta is equal to 45 degree. Calculating virtual number of teeth ZV. ZV is equal to Z1 upon cos delta. Z1 is actual number of teeth and delta is semicone angle for the gears, which is 45 degree. Therefore ZV is equal to 24.042. Step 6, calculating Lewis form factor. As all the factors for meter gear are same, therefore Lewis form factor is also same for all meter gears. YV is equal to pi into y equal to pi into 0.154 minus 0.912 upon ZV. Hence YV is equal to 0.3646. Setting virtual number of teeth ZV. ZV is equal to Z1 upon cos delta. Z1 is actual number of teeth and delta is semicone angle for the gears, which is 45 degree. Therefore ZV is equal to 24.042. Step 6, calculating Lewis form factor. As all the factors for meter gear are same, therefore Lewis form factor is also same for all meter gears. YV is equal to pi into y equal to pi into 0.154 minus 0.912 upon ZV. Hence YV is equal to 0.3646. Step 7. Material properties. As we are selecting material for meter gear is alloy steel having ultimate tensile strength is equal to 90 kgf per. By substituting all the values in equation, we get design bending stress is equal to 2245.83 kgf per mm square. Step 9. Calculating mean module based on building failure in static condition. MAV is equal to 1.28 into cube root of design torque upon Lewis form factor into design bending stress into psi m into number of teeth on gears, where design torque is equal to mt into kd into k, where kd into k is equal to dynamic load factor, which is equal to 1.5. mt is equal to 97420 into rated power upon rpm. Rated power is equal to 6 and rpm is equal to 585.71, which gives the value of mt is equal to 997.968 kgf into centimeter. By substituting all the values in equation of design torque, we get design torque is equal to 1496.952 kgf into centimeter, assuming value of psi m is equal to 10. By substituting all the values in module equation, we get mean module is equal to 0.463 centimeter. Now by standardizing the module, we get the module is equal to 0.5 centimeter. Now for calculating the value of B, we are using equation psi m is equal to B upon mean module. By substituting the value of psi m and mean module, we get B is equal to 50 equal to 0.5 centimeter. Step 10. Calculating transverse module MT and cone distance R. MT is equal to MAV plus B into sine delta upon Z equals to 5 plus 50 into sine 45 upon 70, which gives value of MT is equal to 7.079 mm. Cone distance R is equal to MT into Z upon 2 sine delta is equal to 5.66 into 70 upon 2 into sine 45, which gives value of cone distance is equal to 85.104 mm. Step 11. Calculating induced contact stress. We are using equation for induced contact stress from PhD data book, in which we are using Young's modulus E is equal to 2.15 into 10⁶ kgf per centimeter square. Hence, by substituting all the values, we get induced contact stress sigma C is equal to 8596.314 kgf per centimeter square. As our induced contact stress is less than design contact stress, thus our design is safe against fitting failure. Step 12. Calculating beam strength of gear tooth Fs. Fs is equal to sigma B into B into Lewis form factor into 1 minus B by R into MAV. Hence, by substituting the values in equation, we get beam strength of gear tooth is equal to 603.1. Step 30. Calculating dynamic load FT. FT is equal to FT plus 0.164 into Vn into CB plus FT upon 0.164 into Vn plus 1.485 into root of CB plus FT. Thus, by calculating and substituting all the values, we get dynamic load FT is equal to 493.83 kgf, as our dynamic load is less than the beam strength of gear tooth. Thus, our design is safe against dynamic load. Step 14. Calculating wear strength. Fw is equal to 0.75 into B into Q into T into K upon cos delta. By substituting all the values, we get Fw is equal to 660.57 kgf, as our Fw is greater than Fd, thus our design is safe against fitting failure. Step 15. Design of shaft. Selecting shaft material as plain carbon steel of grade C45 having yield stress SYT is equal to 360 Newton per mm square, and selecting factor of safety is equal to 5. Calculating permissible shear stress tau is equal to 0.5 into SYT upon factor of safety, which gives value of tau is equal to 36 Newton.
Now calculating diameter of shaft. Using the relation tau is equal to 16 into mt by pi d cube, that is tau is equal to 36 and mt is equal to 997.968 into 10 raised to 2. From this equation we get d is equal to 24.169 mm. Now standardizing the shaft diameter from PhD data book and selecting 25 mm diameter as a shaft diameter. Following are the gear tooth proportions. First one, transverse module MT equals to 7.079 mm. Second one, cone radius R equals to 85.104 mm. Third one, reference diameter D is equal to MT into Z, which is equal to 120.34 mm. Fourth one, tip diameter equals to MT into Z into 2 cos delta, which is equal to 130.35 mm. Face width B equals to 50 mm. Number of teeth Z, capital Z is equal to 17 mm. Height factor F0 equals to 1. Reference angle delta equals to 45 degree. Addendum HA equals to MT, which is equal to 7.709 mm. Dedendum HF equals to 1.1236 into MT, which is equal to 7.95 mm.
Bearing selection. In worm differential drive, we are going to use two deep groove ball bearings. First one to support the input shaft connected to worm, and second one to support output shaft connected to bevel gear. Bearing selection is basically depend on forces acting on the shaft.
Horizontal loading, and we get the reaction, horizontal loading reaction as 334.25 Newton. After that, considering vertical loading, and we get vertical forces equals to 146.65 Newton. Now calculating the resulting forces is equal to root of RH1 the whole square plus RB1 the whole square, or RH2 the whole square plus RB2 the whole square, root of. Therefore the equivalent load P, which is equal to C greater than or equal to 16.036 kilonewton, we select the shown here. Analysis of critical components. The following are the critical components. First one is worm. The figure to the left indicates stress analysis. The figure to the right indicates strain analysis. The figure to the left indicates analysis of worm. Similarly, the figure to the right indicates the stress analysis of worm wheel, which is the second component. Similarly, the strain analysis and the total deformation analysis of worm wheel. The third one and the last critical component is the bevel gear or metered gear, with stress analysis